Welcome to Study Loop.
So in this problem, we are given with the reaction of the decomposition of molecular iodine into atomic iodine. And here the values given are the temperature as 800 K and the value of Kc as 3.1 times 10 to the power minus 5. So in first part of this problem, we have to find out which species, whether molecular iodine or atomic iodine, will predominate in the equilibrium. So to know that, first you have to write down the equilibrium constant expression for this reaction. So that will be the concentration of the product, which is atomic iodine concentration, and here will be power of 2 since the coefficient is 2 here, and over the reactant concentration, which is the concentration of molecular iodine. And the Kc value here is given as 3.1 times 10 to the power minus 5, which is very small compared to 1. That means the value of this ratio here is very smaller than 1, means um, the value in the numerator is way smaller compared to the value in the here as the concentration of the molecular iodine. That means the concentration of the molecular iodine is very large compared to the concentration of the atomic iodine, and that's why in the equilibrium the species molecular iodine will predominate. Now, in the second part of this problem, we have to find out which reaction, whether forward or backward reaction, will have um, larger rate constant. So, for this, if we consider the forward rate constant as Kf, then the forward reaction rate will be Kf times the concentration of um, the reactant I2. And if the backward or reverse reaction rate constant is Kr, then the reverse reaction rate will be Kr times the concentration of the product, which is I over and 2 as a power of this. So this is the forward reaction rate and this is the reverse reaction rate, and at equilibrium these two rate will be equal. Now from this equation, if we rearrange this as Kf over Kr, it will be equal to the concentration of the product over the concentration of the reactant. This is again the value of the equilibrium rate constant Kc, which has a value of 3.1 times 10 to the power minus 5, which is very small compared to 1. That means this ratio, the forward rate constant over the reverse rate constant, has a value of which is very smaller than 1. That means Kf is smaller than Kr, or the reverse rate constant is larger than the forward rate constant. So the answer to the part B is reverse rate constant, or the reverse reaction rate constant is larger than the forward reaction rate constant.